Welcome to VEDET, Viewpoint Equivariance for Multi-View 3D Object Detection. To give you a quick summary, our work addresses the problem of multi-view 3D object detection, where given multi-view images with poses, the detector outputs 3D bounding boxes and class IDs for objects in the scene. Our proposed VEDET exploits 3D multi-view geometry to improve detection performance through viewpoint equivariance, such that predictions from different coordinate systems are geometrically consistent. Specifically, VEDET has a data-style object detector with an image encoder, two geometric encoders, and a transformer-based decoder. The image features of multi-view images are fed into the decoder as the keys and values, while the positional encodings are constructed from the camera parameters to reflect 3D perspective geometry. On the query side, queries are constructed from learnable 3D query points together with selected query views. Finally, during training, our proposed viewpoint equivariance loss would encourage the model to predict 3D bounding boxes to have multi-view consistency, which leads to better detection performance. As a quick glance at the performance, we achieve state-of-the-art detection on new scenes, a large-scale driving dataset. Now let's dive into more details. First, our work focuses on two main challenges in multi-view 3D object detection, namely model architecture and learning objective. Previously, multi-view 3D object detection is done by first performing monocular detection on each image and followed by a heuristic post-processing to merge the predictions. This has some clear drawbacks, such as limited single-view context and depth ambiguity from monocular images. Our VEDET, like some recent works, adopts a data-style transformer which directly reasons from multi-view context with our proposed novel 3D positional encodings. To take a closer look, image features are extracted from the multi-view images, which are flattened at the spatial dimension and concatenated as the key and value tokens to the decoder. For each token, we calculate the corresponding camera ray that originates from the camera center and points to the 2D grid location. And then we use a geometric encoder to map the ray, camera quaternion, and camera translation into a 256-dimensional vectors as the positional encoding. The geometric encoder consists of a Fourier transform followed by an MLP. We found that this input-level inductive bias and geometric encoder greatly help the model to learn good localization. As for the learning objective, previous methods regress the 3D bounding boxes in typically just one single coordinate frame. Here, we propose to also regress the boxes in multiple virtual frames with viewpoint equivariance. We found that this would exploit more meaningful signals for the model to learn 3D proper geometry. To see what this means, in addition to the single coordinate frame that people would normally use, typically a global frame attached to a LiDAR mounted on a car, for example, we would also decode boxes from a few other virtual frames. For example, 2 in this case, such that the boxes predicted in these 3 frames should be geometrically consistent, such that their coordinates only differ by the relative transformation between the viewpoints. This mechanism is implemented via viewpoint conditioning, where each query comes from a 3D query point and a query view. The set of 3D query points are learnable, while multiple query views are randomly sampled at training time. To implement the viewpoint equivariance loss, we calculate multi-view targets from the ground truth, as shown here, and consider them as superboxes. for both the Hungarian matching and training. We use superbox prediction and targets to calculate the optimization loss and one-to-one box regression loss. We found that jointly considering multi-view entities as superboxes is also key to achieve the viewpoint equivariance. Now let's look at some experimental results. As mentioned, we achieved state-of-the-art detection on new scenes, outperforming a closely related prior work called Petter V2. In our extensive ablation studies, we show the effectiveness of the proposed components. Most importantly, the 3D positional encodings of camera geometry with Fourier transform, and adding the virtual views while paying the viewpoint equivariance loss. Please also see our paper for more detailed analysis. We would also like to further emphasize the role of our proposed viewpoint equivariance. Here, the orange line represents adding the same amount of query points without viewpoint equivariance, while the purple line enforces this. We can see that compared to the blue baseline, simply adding more queries has limited effect, whereas our proposed viewpoint equivariance brings meaningful geometric learning signals to boost the performance. Finally, we show that our proposed 3D positional encoding better guides the attention from the decoder to the image features. As in this example, the model is able to perform better cross-camera reasoning on relevant areas compared to Petter V2. Thank you for listening. Please try out code at this QR code and chat with us at our poster session.